Hopefully you worked through this on your own. If you haven't, make sure you push pause right now. I am going to work through this example and go through approximating using differentials. On both of these approximations, I do want to know, or I do want to start at 3 on both of these approximations because it says that knowing h of 3. Let's compute h of 3. All we would do is take 4 times 3 squared plus 1 times 3 minus 7. I'm just plugging it into this original function right here. So h of 3 would be 32. The other thing I'm going to need is h prime of 3. In order to get that, I'm going to have to calculate the derivative. H prime of x is equal to 8x plus 1. If I plug in a 3 into the derivative, 8 times 3 plus 1 is 25. Therefore, h prime of 3 is 25 and h of 3 is 32. If I want to approximate h of 3.1, what I'm going to do is I'm going to take h of 3 plus h prime at 3 multiplied times the change in x. So if you're not following, hopefully you are, but you're going to take your y value at 3 plus a corresponding change in y value. That corresponding change in y value is our differential dx multiplied times the derivative of our function at our starting value. In other words, it's h prime of 3 multiplied times dx. In my case, since we started at 3, that change in x is simply a 0.1. So going from 3 to 3.1 is a change of 0.1 in the x value. Now I can plug in all of this stuff. I should have really been putting in not the equal to sign, but the approximate sign. I will keep doing that. Okay. Now we've put in the approximate. H of 3 would be equal to 32, like we have up here. H prime of 3 is equal to 25. And once you've done that, 32 plus 25 times 0.1, 32 plus 25 times 0.1 should give you 34.5. The approximate value at 3.1 would be 34.5 then. You can punch this into your calculator too. 4 times 3.1 squared plus 1 times 3.1 minus 7. And the calculator gives out an h of 3.1 of 34.54. So notice the differential approximation was very close to the calculator's output. The next question is h of 2.95. We're going to go through the same process of approximation for 2.95. In this case, we have to be very careful. We are still starting at 3, but in this case, we went down to 2.95. So the change in y value is going to correspond to a same thing, h prime of 3 multiplied times a dx. But the dx in this case is going to be negative. So we're going to have h prime of 3 multiplied times negative 0.05. Since we went down, we have to use a negative. Since we're under 3, we have to utilize a negative. H of 3 is still 32. H prime of 3 is still 25. Now I'm using negative 0.05. 32 plus 25 times negative 0.05 becomes 30.75. So the approximate value of 2.95 using tangent lines is 30.75. When I say using tangent lines is the same thing as using differentials. So there you go. When you plug in 2.95 into your calculator into the original function, h, so 2.95 into that function, what you'll see is your calculator gives out h of 2.95 is exactly equal to 30.76. Again, we're very, very close to the value of the actual function with our approximation. So our approximation does a pretty good job when the x value is close to the x value you're starting with. That's how we approximate these values using differentials. In the previous 2 examples, we had a polynomial function or a trig function here that was explicitly defined. There's some other things we can do with these differentials where I might not have a function explicitly defined. We're going to take a look at that in the next couple of examples.